Imagine trying to land on a world without a solid surface, where temperatures and pressures could crush and melt any technology we send. This scenario challenges not just our bravery, but also the limits of modern space engineering. Unlike terrestrial planets like Earth, which have solid surfaces, Saturn is primarily composed of hydrogen, with significant amounts of helium and traces of other gases such as methane and ammonia. There isn't a solid surface on Saturn, just a gradual transition from gas to liquid under extreme pressures and temperatures as one delves deeper into the atmosphere. Saturn's atmosphere is notably dynamic and hostile, characterized by strong wind currents, gigantic storms, and intense climatic variations. Notable examples include the hexagonal storm at the North Pole, a meteorological phenomenon that illustrates the complexity and energy of Saturnian weather. This atmospheric volatility poses a significant barrier to any landing attempt, as it involves confronting abrupt changes in atmospheric conditions, which can vary rapidly in terms of wind speed and direction. As a spacecraft attempts to descend into Saturn's atmosphere, it would encounter increasingly extreme conditions of pressure and temperature, a common phenomenon in the gas giants of our solar system. On Earth, we are accustomed to an atmosphere whose pressure is ideal for life as we know it. But on Saturn, atmospheric pressure increases exponentially as one goes deeper. This pressure can reach levels so high that any material currently available for spacecraft construction would be crushed, like paper under a hydraulic press. Similarly, temperature also increases steeply with depth in Saturn's atmosphere. At the top of the atmosphere, temperatures are extremely cold, but they become incredibly hot as one approaches the planet's core. These temperatures can easily exceed the resistance limits of materials known to human engineering, melting essential spacecraft components and compromising their structural integrity and functionality. Besides the physical difficulties imposed by pressure and temperature, the rapid changes in these conditions represent an additional challenge. A spacecraft would need to be extremely robust and capable of adapting quickly to avoid structural or system failures as it descends deeper. Currently, space technology lacks materials or systems that can tolerate such extreme variations without sustaining critical damage. Saturn, with its immense mass, exerts a stronger gravitational force than Earth, posing a significant challenge for space exploration. Standard landing and maneuvering operations, which are relatively more controllable on smaller celestial bodies, or those with weaker gravity, become extremely complicated and risky on a planet with Saturn's gravity. The intense gravitational force can rapidly accelerate a spacecraft, pulling it into the atmosphere at a speed that makes controlling the trajectory difficult. If we consider a point on Saturn where the atmospheric pressure is similar to sea level pressure on Earth, the gravity there would be about 10.44 meters per second squared. For comparison, Earth's sea level gravity is about 9.81 meters per second squared. This means that gravity on Saturn is about 6% stronger than on Earth. If you weighed 100 kilos on Earth, on Saturn you would weigh about 106 kilos, assuming you could stand on a solid surface to measure that weight, which, as we've discussed, is not the case on Saturn due to its gaseous nature. In addition to the problem of acceleration, Saturn's strong gravity also amplifies the effects of atmospheric drag on the spacecraft. As the craft penetrates deeper into the planet's atmosphere, the combination of high velocity induced by gravity and increasing atmospheric density can result in significant aerodynamic forces. These forces can lead to extreme mechanical stresses on the spacecraft's structure, demanding thermal and structural protection technologies that are beyond current capabilities. Managing atmospheric entry under such conditions would require extremely advanced and robust propulsion and control systems to counteract the gravitational pull and ensure a controlled and safe descent. The lack of such technologies in current space engineering makes the mission not only dangerous, but also technically unfeasible. Moreover, any failure in systems during this critical phase of descent could result in a total mission loss, with the spacecraft being destroyed due to overheating or impact with the denser layers of the atmosphere. Therefore, Saturn's gravitational forces pose a significant barrier to direct exploration through landings. Until we can develop technologies capable of mitigating these extreme risks, the exploration of Saturn should continue to focus on orbital missions or flybys, which allow for detailed studies without exposing spacecraft to the dangers of its potent gravity and hostile atmosphere. Saturn is truly one of the most challenging places to consider for space landings, with the technology we have today. If you found it fascinating to learn about these nearly insurmountable obstacles and the wonders of our gas giant, don't forget to like this video, subscribe to the channel for more content like this, and hit the bell so you don't miss any updates. Oh, and of course, share this video with friends who also enjoy science and space. Until next time, explorers. Keep looking at the stars and wondering, what else is out there? If you enjoy imagining the possibilities and exploring other perspectives of the universe, don't miss our latest video. In it, we dive into the paradoxes that continue to intrigue scientists to this day. We discuss how these issues challenge our understanding of reality. Click now to find out more, and join the conversation in the comments about which paradox intrigues your mind the most.